if you can see few things which are there in this, do you see that there's a setup here, right? There's a setup. What is the setup for? The setup is for a ripple tank, okay? Ripple means very small waves, okay? So we are going to create very small waves, and then we will put obstacles in between, okay? These obstacles, when we put in between, so the waves will have some effect on them. And that is, we are going to study what effect happens. Clear? But this point is clear? Okay. So if you can see on the screen, there is a tank. So in that tank, there is water. Okay? There's water. So water is the one which is going to create those tiny waves. The ripples are being produced here, right? Who is creating the ripple? Do you see? There is a vibrating block to produce the ripples. Okay. How is the vibrating block working? Because there is a motor which is used for the vibrations. Okay. So that motor works. All right. Then just to see it clearly, there is a lamp here. All right. Then there are wave shadows which are forming below. So there is a wave and the shadow is underneath here. Okay. And you see there's this person who's holding something which is called as a stroboscope, which is a spinning disc, so that this person can freeze the motion of the wave and see it and observe it. Point is clear. The setup is clear. Okay. Now from here, let's understand the word reflection. Okay. So a vertical surface is put in the path of the waves. Okay. And the waves are reflected from the surface at an angle as they strike. So what do I mean by that? You will see this. This is what happens in reflection. First of all, what kind of obstacle is being put is this. This is the obstacle. What do you see? There's a vertical plate which is being put. Can you see that? Shamik, if you're doing anything else, please stop it. Okay. Do you see there is a vertical thing which is kept in between? Okay. For, let's see what we do for refraction. I'm just going to explain everything. What?
What vertical thing? The line.
So just understand this one by one. This figure that you see, we are into that whole setup. And if you can see this, this is what you will do for reflection, for analyzing the wave for reflection. This part is clear. Here you are analyzing the wave for reflection. What are you doing? Do you see there is a vertical plate here? Obstacle is like this. And you will analyze the effect based on, I'll show you what analysis we do. But did you understand that there's a vertical plate kept? Okay. In the second case, this is for refraction. What is kept here? For refraction, there's a piece of plastic which is kept here. Okay. Ripple slow in. Okay. We'll see what is the effect later. But this part is understood. There's a difference between this figure and this figure. Obstacles, how the obstacles are placed. Do you understand this? Right? We will see the effect later, but how we are placing the obstacles is what you need to understand first. Okay. And there's a third phenomena, which is diffraction. And for diffraction, the waves are kept in, the obstacles are kept in this way. For diffraction, obstacles are kept in this way. Did you understand? This is how we are placing the obstacle for understanding the three phenomena. Simple. For the first one, there is a plate. For the second one, there is a plastic plate at the bottom. And for the third one, there is a plate with a gap in between. And you increase and decrease the gap and you understand. You try to analyze. Clear? Okay, next. When you see, let's go back to the reflection. In reflection. Huh?
I don't think we have all this.
You have? Very much. What are you saying? This is such an important topic. Wave effect. There are so many past paper questions on this.
Yeah. But
Hmm?
I don't see it in the book.
Okay, but still we are studying it because it is, I don't know about the book, but you will be taught and you will face a lot of questions based on this, okay? It's there in the syllabus. Maybe there are certain topics which are not there in the book. I don't know, but it's a very much part of the syllabus, okay? Okay?
Yeah, I see it. Yeah, it says.
There, very much there, yeah. इसके बिना इस पे तो जरूर एक क्वेश्चन होता ही होता है, okay? Okay, so what we see, what exactly happens when it is this situation here? See, the vertical surface, which is this one, right, is put in the path of the waves. So what will happen? The wave will they will hit this vertical surface. When they come and they will hit the vertical surface, after that, after hitting it, they will get reflected. The waves are reflected. You know that, right? This everybody knows. Waves are going to bounce away from the surface at an angle that as they strike. So you know that the law of reflection, angle of incidence is equal to angle of reflection, right? So if you see it in the picture here, the waves are coming like this. This is how they were coming. They got stuck. They strike the surface and they take an angle. Okay, this is how it is observed in the shadow. This is the shadow of it, how it is observed. So what happens if you see, if this is the striking surface, the wave came in like this and it bounced back in this way. This angle is equal to this angle and they're going to be equal angles. This is what we observe in the ripple tank, in the shadow. Clear? First part is clear. So 3 things for you to remember. First of all, you have to know the entire setup for the ripple tank. How do we analyze the phenomena of reflection? We put a vertical plate, right? When the wave is going to hit the vertical plate, it is going to get reflected at the same angle as it strikes it, right? And this is what you observe in the shadow. Waves are coming like this and they're getting hit and they're bouncing back at a certain angle. And that angle is shown here. The angle of incidence of each wave is equal to angle of reflection of each wave. Clear? Clear? This phenomenon is understood. Now we move to diffraction. Any confusion in this? I hope there's no confusion.
No.
Okay. In diffraction, you can see that there is a piece of plastic which is kept in between at the bottom, right? The piece of plastic ka sirf itna hi kaam hai that it is going to just create some disturbance in that water. Now, for you to understand here, is there any observation that you see? Do you see that the waves here were very, they were stable kind of. They were just waves like this. But from the part when the plastic started, okay, the depth of the water was less, isn't it? Because of the presence of plastic. Here the depth is more. So here it has become shallow water, right? And the moment it is shallow water, look at the waves which is being created here. Kya ho raha hai waves ke andar?
More frequent. I guess the waves are more frequent.
No, actually it is trying to show that the in shallow water they are slowing down. It's just to show that they are slowing down at this particular part, right? So first you observe there's a difference, right? There's a difference here and here in the 3 parts, okay? What you need to keep in mind is there's a plastic which is kept in between at the bottom for refraction. And on top of that, whatever water is there, that will have a certain change. That you will see that the water, in the ripples, there will be some change. So basically the ripples will slow down when there is a water. I mean, there's a shallow water. So let's read this. A flat piece of plastic makes the water more shallow. This slows the waves down. When the waves slow, there is a change. They change the direction. The effect is called refraction. Now, iska figure kaisa hoga? Let's see. What happens exactly at this point? When we observe in the shadow, this is what has been observed. You'll see it in the next picture now. You see this picture? Look at the shadow. This is where the shadow shows that beneath there was a plastic piece which was kept, because of which when the water reached above the plastic piece, it was like this, right? So basically here they are slowing down because of the presence of plastic and shallow water. And then once they are out of this range, they're back to normal. If you can look here also, out of the range of this plastic, they're back to normal. Here also, correct? Okay, now? All right. Now the next phenomena, which is the just a minute. I'll just bring it here. Now let's understand why exactly this happens. Why exactly this whole thing happens. You know that speed is equal to frequency into wavelength, right? You know that speed is equal to frequency into wavelength. We learned this, right? Speed is equal to, speed was velocity, right? Is equal to frequency into wavelength, f into lambda. This is something we learned earlier. Speed is equal to frequency into wavelength. Concentrate here, Shomik. So, and read this. Let's read this together.
So just a symbol for lambda. Yeah,
lambda is
the side with steel thing.
Now, you know that the waves are they're all the time oscillating. They're going up and down all the time at the same frequency all over. Okay? So when they slow, the wave fronts close up, they come close to each other. When they're slowing down, frequency is the same all the time. But when they're slowing down, they close up. That follows that the wave equation, which are written here. As the frequency is unchanged, a decrease in change must cause a decrease in the wavelength. That's why you see the wavefronts are smaller and smaller. From the last diagram on the opposite page, you can see that if the wavefronts close up on each other, their direction of travels must change unless they're traveling at right angles to the boundary. Which means that when they are coming here, frequency is something which is not going to change. But speed and wavelengths, they are things which are going to change. And as we said, as on top of the shallow, when they're in the shallow water, the speed is reducing. So when the speed reduces, wavefronts, the frequency is same, then the wavelength, what happens to the wavelength? The wavelength also reduce. That's why you see smaller waves here. Clear? That's why you see smaller waves. So, and as they are hitting this going above this whole thing, there is a change in their speed. They slow down. Clear ho gaya? Right? All right. Now let's come to diffraction. First of all, what is diffraction? Any idea what is diffraction? No idea. Okay. In this figure, do you see that before these two gaps, let's look at the first figure first. There's a small gap. And before this obstacle, the waves were coming absolutely straight. Okay. Now what happens? After that, there's only this much gap. There's a very small gap. And the wave needs to come out of that. So the obstacle, there's an obstacle, there's a small gap. Do you observe how they're rounding up after that? Right? So they spread out, these waves, they spread out as they're passing through the gap. So what happens? This is an observation. This is what has been observed, that when there is a wave ripple and you put an obstacle with a gap. So what you see that from that gap, the waves they're like kind of bending. They're bending. They make a round shape and they're bending. But as they're spreading out through, as they're coming out, they spread. So if you can actually see this, this is what I'm talking about. Here there's a gap. Here, till here they were straight. After that, they're bending. When they're coming out, they're bending, right? This is what is bending. But as they're moving ahead, they're spreading out. The bend is still there, but they're spreading out. Baat samajh aaya? But do you see that there is a difference here? Can you tell me what is the difference?
The smaller the gap, more curved the wave is.
The smaller the gap. And if you observe the length of the gap, if you see this is very important point and you will get a lot of questions on this. This gap is approximately the gap, the same gap as this much of wavelength. Which means this whole phenomena of bending is called as diffraction. Bending through a gap. The waves bend through a gap. That's diffraction. Okay. And if you see this, the size of the gap has a big role to play here in diffraction. Okay. So if the size of the gap is the same size as the wavelength, then the diffraction is significant. Okay. Jitna zyada gap, utna kam diffraction. Clear? More the gap, less is the diffraction. In the second figure, now let's see. In the second figure, gap is much more than the wavelength. Much more than the wavelength, right? So the diffraction, there is a bending happening, but only at the edges. There's a bending happening, but only at the edges. So what do I understand from here? What do I understand from here? First, what is diffraction? So waves bend round the sides of an obstacle, right? And they spread out as they pass through the gap. This whole phenomena is called as the diffraction phenomena, that waves will bend. Bending of waves is diffraction, okay? Second, how much is bending important? How much is, how do we change this bend? So if you increase the gap to more than the wavelength of the wave, then the diffraction will start reducing. It will be less diffracted. And if your diffraction is, if your gap is same as the size of the wavelength, then there'll be more diffraction. Clear? Samajh mein aaya? So smaller the gap, more is the diffraction. Bigger the gap, less is the diffraction. I hope this part is clear. Okay. If I wanted more diffraction in the second case, then what do I do? If I want more diffraction, case number 2, what do I do?
Lessen the gap in the waves.
Lessen the gap in the waves or lessen the gap of the obstacle?
If you can lessen the gap in the obstacle, then do that.
I can lessen the gaps in the obstacle. What else? What else can I do?
Wavelength closer.
What do I do with the wavelength? I want to keep the gap the same. Then what do I do with the wavelength?
Yeah, you lessen the wavelength.
मैंने gap रखा है बड़ा, but if I lessen the wavelength, then
by placing an object.
By placing an object, I want to keep the object the way it is. I do not want to place anything else. Ab kya karo? I want to still have a better diffraction here. What do I do?
Smaller, narrower gap.
I don't want to change the gap.
In the waves, not the gap.
So when you're talking about waves, then you should say the word wavelength.
Yeah, wavelength, smaller wavelength.
Smaller wavelength, तो
lesser, whatever.
Are you sure? No, it's not right. How is it smaller? How will it be? What is my purpose for better diffraction?
The gap between the waves is, if it's the same as the gap in the obstacle, then there'll be a lot of diffraction. And as you widen the gap, there will be lesser diffraction. So,
But I think you did not understand my question. My question is, in this case, this length, that wavelength, and the gap were almost similar, because of which there was a huge diffraction happening. Okay.
yeah.
But what do I make? What changes do I make in our second case so that I get a good amount of diffraction?
Yeah, got it. Okay, you widen the wavelength.
Either I increase the wavelength to almost this much, that's one point, or I reduce this to almost the same level of the wavelength. Do tarike. So if my question was, if I do not want to change anything in my obstacle, then how do I increase the diffraction? Trisha, how do I increase the diffraction? I don't want to change the obstacle at all.
I didn't understand the question.
Okay, my question once more. In this case, you see that the wavelength is this much and the obstacle is this much, the gap in the obstacle. So there was a lot of diffraction. I want to achieve the same kind of diffraction here also in the second case. What all things can I do? I want to get a good diffraction here. Somehow I need to make this gap and the wavelength equal.
Oh, I don't know.
No, I'm saying that if I want to have more diffraction, I have to make the wavelength and the gap equal. Then only it is possible, right?
Yeah.
So how do I make the wavelength more? By making more gaps in the waves. Yes. I increase the wavelength of the wave. That's one way. Another way is I reduce this. This should be reduced. The gap should be reduced here. There are only two ways, right? Clear, Abhi? Trisha? Sure?
Yeah. Yes.
All right. Sure. Write it in your notebooks. Say whether each of the following effects of B to E above is an example of what?
Above where?
Okay, I'll tell you. Wait. This has something else connected to. About these. So you have to tell me one by one, which one is reflection, which is refraction, which is diffraction. Tell me.
First one is reflection.
Okay. Second one.
Refraction.
Light bends as it passes. Okay. Okay. Sound bends around obstacles such as walls and buildings, which is why you can hear around the corner. Sound can only do diffraction.
Oh,
So
refraction.
Bending means bending around obstacles. Then what is it?
Refraction.
That is diffraction. Diffraction. This phenomena which we just learned.
Yeah.
DIFF.
Right.
Got it now?
Yeah.
Next, light spreads when it passes through tiny holes and slits. This suggests that light must have much shorter wavelength than sound.
Diffraction.
This is diffraction. Next. Some radio signals can bend around every very large obstacle, such as hills. This suggests that radio waves must have long wavelengths. Which phenomena?
Diffraction again.
Again, diffraction. Samajh aa gaya? What needs? Bending means diffraction. And passing through something means refraction. Bouncing back from something is reflection. Clear hua? On the right, waves are moving towards a harbor. What will happen to waves striking the harbor wall at A? At A, what will happen?
Reflect.
They will reflect. Very good. Because wall is like a vertical obstacle, right? Okay. What will happen to the waves slowed by the submerged sandbank at B?
Refraction.
Very good. Very good. What will happen to waves passing through the harbor entrance at C?
Diffraction.
Diffraction.
Superb. Very good. If the harbor entrance were wider, what difference would it make?
Diffraction.
What difference would it make? It's diffraction only.
It wouldn't,
One sec. It would be this thing. It would be more diffracted.
it would be more straight. It wouldn't curve around the edges.
It won't curve around the edges. It will only curve around the edges. It won't be, it won't be. So what exactly is happening? Less diffraction.
Yeah.
Less diffraction, okay? Right? So lesser diffraction comparatively.
Yeah.
Okay, this part is understood?
Yeah.
Okay. Okay. Our next topic is basically it is about nature of the sound waves. Few things that we need to understand. All right, so I'm just showing you one picture. Tell me, what do you see on the screen? Do you see that there are compressions and rarefactions? Compressions and rarefactions. There's a loudspeaker. From the loudspeaker, there is a vibrating cone in the loudspeaker. Loudspeaker से क्या निकलती है? आवाज निकलती है? We hear sound from the loudspeaker?
Yeah.
Yes, all right. So how, when sound is being created, there's something which is vibrating inside the loudspeaker? Okay. Because of the vibrations, what happens? What happens to the air around it? They start vibrating.
Yeah.
The air molecules start vibrating, air particles start vibrating. When they vibrate, we learned about this in the previous class, that what kind of what kind of wave is it? It is longitudinal wave. So there will be compressions and rarefactions in the wave. Compressions and rarefactions in the wave. So do you see that happening here also?
Yeah.
Right. So one compression, starting of one compression to the end of one rarefaction makes one wavelength. This part is clear?
Yeah.
This part is clear? Okay. So, and this is also called as, drawing a wave front. So this part is understood that there are compressions. How is sound being created? There are compressions and vibrations all over because it's a longitudinal wave, right? And do you understand that sound is being created due to vibrations? Because of vibrations. Sound is only created because of vibrations.
Yeah.
Right? Okay. So we learned already that sound is a longitudinal wave. Right? Then can sound travel through a medium?
Yeah.
It only travels through a medium. Will it travel in vacuum?
No.
No. Can sound waves be reflected, refracted, and diffracted?
Yes.
Can be reflected, refracted, and diffracted. All three, right? All three phenomena, right?
Yeah.
Okay. If I want to show a sound wave, now one more picture which I want you to understand. Okay, look at this picture. What is it about? So if you see, there are two rubber bands. There's an electric bell. It's a glass jar. There's a battery inside, and there's a vacuum pump. Right? This bell is ringing. So when the bell rings, you're able to hear. Okay. So there's a vacuum pump through which all the air has been extracted. All the air has been removed. What will happen after that? I can see it is ringing. Will you hear the sound? Will you hear the sound?
No.
Why can't you hear the sound?
Because there's a vacuum around the bell, so the sound cannot travel to your ears.
No sound because there is no medium. Right? No sound as there is no medium here. What is the medium? No medium is no air particles.
Yeah.
Vacuum is not a medium. Vacuum is there's no air.
Vacuum is no medium.
Vacuum is no medium. Yeah. All right. Now, next. If I want to display sound, is there anything that we can display the sound with? So there is an instrument called an oscilloscope. Here. Cathode ray oscilloscope. Okay. All right. Can you, I think you can read from this, understand from the figure itself, very explanatory. What happens? You're speaking on that microphone, that's a mic. What do you get on the screen? See and tell me.
Waves.
Okay. So when you speak on that microphone, this whole instrument is converting all that sound that you're speaking into certain waves, and you can see the waveform in that screen, right?
Yeah.
Okay. So what happens in that microphone? You are speaking. So when you're speaking in that microphone, there is a crystal, there is a metal plate inside. Okay. That metal plate starts vibrating. Okay. Now, as the vibrations are being changed, so you increase the sound, you decrease, as you're changing, whatever you're speaking, that is changed into an electrical oscillation. It is changed into an electrical signal. And this oscilloscope is using this signal to make this up and down oscillation on the screen. Do you see that? All right. So what exactly is happening here? There is what you see is called a waveform. So what does oscilloscope provide us? It provides us a waveform. And you must have seen something like this before. Kahan dekha humne?
What?
This kind of a structure. Kahin dekha hai pehle?
In hospitals.
In hospitals, yes. Where, Risha?
Like a heart monitor?
Absolutely. Heart beats, so there's sound. So that sound is taken into that microphone which is attached. And from that, there's a small microphone which is attached. From there, it converts all the sound into this waveform. And what if somebody dies? So what happens after that? What happens after that? No sound. If somebody dies, heart stops beating, no sound. So there is a straight line. ऐसे दिखाते ना, somebody dies in movies, it shows like a straight line. No more ECG, right? That's how they show. Exactly what is here. Got it? Okay. Are there any ways of reducing the sound? Suppose I stay in a place where there's a lot of sound. Is there any way that I reduce the sound? What are the ways so that I can reduce the sound?
Block its path.
Block its path. Okay. I stay in near the highway. So there's a lot of sound which comes to my house. So how do I reduce that sound? What are the ways?
Curtains.
Curtains, right? Because why curtains? Why did you say curtains?
They absorb sound.
Absorb sound. What else? Curtains or kya hoga?
Mats, rugs.
So you mean to say carpets?
Yeah, carpets.
Okay. Then what else? They absorb. So curtains, carpets, some certain furnitures, padded furnitures.
Yeah.
Those which have fabric furnitures, right? Which have a lot of foam in them. So will that also help? Okay.
Yeah.
So these are good absorbers of sound. So in your house, you can use, if you want to reduce the sound, you can use these things, right?
Right.
Right? Okay. Apart from that, this is in the house that you can do. What else? Now I stay right above the highway, so it's so noisy. But the moment I close the window, this window pane, so all the sound goes, most of it. So what are they using here?
The glass.
There are
the glass stops the sound.
special kind of
reflection.
It is something else. It is something else. So I'll tell you what it is actually. This is a glass. So these are called double glazed glasses because what happens here is there's a glass, there's another glass, and they leave some gap in between. That gap, from there, they create a vacuum. They create vacuum and they put foam in between or something in between so that whatever gap, everything is removed. Something they put inside. So what happens? As it is, it's vacuum and there is something inside which is not allowing any of the sound. So even if the glass is able to reach, the sound is able to reach this glass, it won't be able to reach this glass. So when I close the window, because you know that the sound is not able to travel in a vacuum, so nothing is able to cross through. That sound is reduced to a great extent. I hope it's clear.
Yeah.
Right. Apart from that, in big halls and stuff, they use fiberglass. Okay. And these are basically in halls where you need soundproof system completely. There's no noise which should, you don't want any noise. In theaters, you don't want any noise. So they use a lot of fiberglass, which is actually a kind of acoustic diffuser. Acoustic diffuser means sound diffuser. Sound ko wo kam karega. So special material. So 3-4 ways that you have described till now. One is you said use more curtains and carpets and all of these padded sofas and all furnitures, right? Second is using, if the sound is from outside, then we use what kind of glasses? These are called as double glazed glasses. So these special soundproof glasses, okay? And the third is in big movie halls and stuff. So we use these acoustic diffusers, which are made of a special material called as the fiberglass. So that helps in making the sound reduce. I hope it's clear to you. Now your next sheet is here. Quickly answer these.
Oh, Auntie, Just diffraction, reflection, refraction, and waves is not there in the ocean for now. It'll be there next year. It's in chapter 14.
Arey beta, we are studying everything all together, no? We have nothing for this year, that year. We will.
Yeah.
Chalo, do this. Because I want you to start the papers very soon now. Whatever you're able to do now, you do it. Otherwise, rest of the questions will become your homework. Okay? And to be discussed in next class. Your next class is on
Thursday, 1 week later. Done.
all of them. Sorry? You're on mute.
And write them down.
Sorry?
I haven't written it down.
You have to write it. That's what I'm saying. You have to write it.